Hello students and welcome to Chemistry at JP's Academy. Students, in today's lecture we are going to do a very important topic, which is Graham's law of diffusion and effusion. It's a very important topic from the chapter gaseous state or states of matter. So before I start the lecture, I request everyone to please like the video and subscribe to the channel. Now students, what exactly is diffusion or effusion? Let's start with the basics. So students, effusion is the escape of gas molecules. Imagine that you have a container, and in the container we have a diffusion chamber in which we have a tiny hole, and the escape of gas molecules through these holes. Remember, the gas molecules are moving randomly and rapidly. They're colliding with the walls of the container, and there's a tiny hole, so the molecules come out of that hole. That phenomena is called as diffusion. Now what should be what should be noted over here, students, is that the hole should be very tiny, such that the hole's diameter must be smaller than the mean free path. Mean free path of the molecule is nothing but the distance that a molecule travels before any collision. So that what's really happening is, we can say that one molecule or each molecule is coming out without any collision through the hole. That will also help us calculate values. And diffusion, though diffusion and effusion are different, what exactly is diffusion? Is the spontaneous movement of gas molecules from a high pressure to low pressure until the partial pressure is equalized is called as diffusion. We can, however, say that Graham's law is applicable to both effusion or diffusion, and Graham's law says that. So let's say, students, we have a container, and inside the container, or a diffusion chamber, we can say that I have a particular gas, and let's say the pressure inside is more than the pressure outside. So what will happen is, gas molecules will escape out of the container. Then Graham's law of diffusion states that the rate of this diffusion, the rate of effusion or the rate of diffusion is inversely proportional to the square root of the molecular weight of the gas. And now let's say, students, if we have a mixture of non-reactive gases inside chamber. So what if inside the chamber I have multiple gases present and which are not reactive? Let's imagine gas A and gas B. Then the rate of diffusion, let's say RA upon RB, which is the rate of diffusion or rate of effusion of gas A and gas B, will be the partial pressure of each gas, okay, into the the reciprocal of, or you can say inversely proportional to the molecular mass, molecular weight of the gas. So two gases A and B, so the rate of diffusion for A by B will be partial pressure of gas A upon partial pressure of gas B into the molecular weight of gas B upon molecular weight of gas A. Now we can further, students, modify this equation. We know that according to Dalton's law, I repeat, according to Dalton's law, the partial pressure of any gas is equal to the mole fraction of the gas and the total pressure. Now, the first rule that we wrote, that rate of diffusion is inversely proportional to molecular mass, was assumed that this is happening at constant pressure and at constant temperature. So let's say, students, if we have two gases, total pressure being Pt, the partial pressure of gas A given by Dalton's equation is partial pressure into mole fraction into total pressure, and partial pressure of gas B will be mole fraction of gas B to total pressure. And we can substitute that, and we also get the rate of diffusion of A by B is equal to mole fraction of A over mole fraction of B into molecular mass of B upon molecular mass of A. We can also say that this is another way of writing the equation for rate of diffusion of two gases. Now, students, along with that, rate of diffusion also depends on certain other parameters. Rate of diffusion also depends on the distance traveled by the gas. I will just write distance traveled upon the time taken. This is really important for different types of numericals which are framed. Or, students, we can also say, instead of distance traveled, number of moles diffused or effused upon the time taken for that to happen. So the same law in different ways can be expressed like this. Or the volume of gas diffused upon time taken. Now, students, rate of diffusion or rate of effusion is proportional to the velocity of gas molecules. Where actually this expression comes from, it simply comes from the expression of kinetic energy. Students, we know that if I have two gases at the same temperature, they will have the same kinetic energy. So let's say I have two gases at the same temperature. Then I can say that the kinetic energy of gas A will be equal to the kinetic energy of gas B. And kinetic energy, we know, students, is half m1 v1 square. Let's say the mass of the gas A is m1 and velocity is v1. And for gas B, it is half m2 v2. So from here, students, we can get the expression that v1 upon v2 the whole square will be m2 upon m1. Or I can say that velocity is inversely proportional to the square root of the mass of the gas, and rate of diffusion is directly proportional to the velocity of the gas molecules. And this is where we get the relation. I hope, students, we are getting this. Now, let's move ahead with one of the most important applications of Graham's law, which is the successive diffusion and enrichment of lighter components. What exactly is this, students? Let's say I have connected in series over here multiple different diffusion chambers. This can be used to separate gas mixtures. Let's understand how that takes place. Now, let's say, students, in the first diffusion chamber, I have two gases and I want to separate them. How we do this is, now, since there are two gases, let's say gas A and gas B is present inside this particular diffusion chamber. According to Graham's law, we can say that the rate of diffusion of gas A to the rate of diffusion of gas B will be mole fraction of gas A upon mole fraction of gas B into root of molecular weight of gas B upon that of A. Now students, the ratio of mole fraction can also be written as the ratio of number of moles. So this becomes number of moles of gas A upon number of moles of gas B into molecular mass of gas B upon molecular mass of gas A. Now students, this is the rate of diffusion of the gases in the first chamber. Now these gases go from the first chamber to the second chamber, and hence we can say that this rate of diffusion is nothing but the ratio of the number of moles of gas in the second chamber. This is the ratio in the first chamber. Now these gases are now present in the second chamber, and from there onwards it will move to the third chamber. So I can say that the rate of diffusion of the gas in the second chamber, I repeat, the rate of diffusion of gas in the second chamber will be the number of moles of the gas in the second chamber, Na upon Nb in the second chamber, into the square root of inversely proportional to the molecular mass of the gas. And students, from the first equation, we can see that Na upon Nb in the second chamber can be written as Na upon Nb in the first chamber into the square root of molecular weight of gas B upon molecular weight of gas A into, so this was Na upon Nb in the second chamber, into, we already have molecular weight of gas B upon molecular weight of gas A. So that becomes the ratio of moles of gases in the first chamber into the square of Mb upon Ma excuse me. Similarly, let's say this is equation number 2. Now in the third chamber this continues. We can say that, students, in the third chamber the rate of diffusion of gas, so Ra over Rb, will be the number of moles of the gas, the ratio into square root of the inverse of the molecular weight of the gases. And from the second equation, we know that this is the number of moles of gas which are going from the second chamber to the third chamber. And I can write Na upon Nb in the third chamber as Na upon Nb in the first chamber into, there was square over here, this will become raised to 3, and this will be the number of moles going on to the fourth chamber, so on and so forth. So if we attach such n number of chambers, final expression can be written as Ra upon Rb in the nth chamber is equal to, sorry about that, is equal to Na upon Nb in the first chamber into the root of Mb upon Ma the whole raised to n, and that is equal to Na upon Nb into n plus 1. Or we can write this as, I'll write the expression in one more different format. This can be written as n minus 1, n minus 1, considering the nth chamber number of moles. So these students can be used in order to separate a mixture of gases. Students, I hope everyone got the lecture. There are a lot of numericals which can be solved on the basis of Graham's law, and usually in IIT JEE Advanced we have numericals which they ask. The syllabus states of matter was removed from JEE Mains, and hence states of matter is not a current topic which is present in JEE Mains and NEET scope. However, this is a very important topic for all the others, for JEE Advanced and for many other exams such as BITS Pilani. So students, if you need good questions on this, please let me know in the comment section. I'll have a separate lecture where we'll solve numericals based on Graham's law of diffusion. Students, thank you so much for watching. This is JP Sir. This is JP's Academy within Sir. Thank you so much.